Lesson 7 of Chapter 1 is on inverse relations and functions. Our first objective is to use the horizontal line test to determine if functions have an inverse. And then the second thing we're going to do is find the inverse of a function algebraically and also discuss them graphically. So if you look at these two tables represent an inverse relationship. Table A on the left shows that if you buy 3 tickets, it costs you $6. If you buy 4 tickets, it costs you $8. Well, now if you look at Table B, the table on the right, this shows you that if you spend $4, you purchase 2 tickets. If you spend $8, you purchase 4 tickets. So those two tables show inverse relationships or inverse relations. You might remember from function work that we have something called the vertical line test, and that tests to see if a graph is a function. We also have something called the horizontal line test, which tests to see if a graph has an inverse. So as you can read here, it says a function f has an inverse function, and this is the notation we use for the inverse, if and only if each horizontal line intersects the graph of the function in at most one point. So, to show you an example of that, example 1 says graph each function using a graphing calculator. I've got that done. And then apply the horizontal line test to determine whether its inverse function exists. Write yes or no. So you can see on part A, we've got the absolute value of x minus 1. If I take a horizontal line, and if I place it here, it obviously crosses the graph more than once, so this does not have an inverse. If you look at part B, if I take a horizontal line, no matter where I put it, it never crosses the graph more than once. Now some people say, what if you put it right here because it appears to be flattening out? Well, it's still increasing as you work left to right. That graph is still increasing entirely on its domain. So no matter where I put this red line, it's always touching the graph just once. So this does have an inverse. So then we talk about if a function passes both the vertical and the horizontal line test, then it's said to be a one-to-one function. And what that means is for every input or element in the domain, there's exactly one output or element in the range. And then for every output, there's also exactly one input. So that's what it means to be a one-to-one function. So example 2 now leads us to the direction, say, determine whether f has an inverse function. We'd apply the horizontal line test to this. If I were to graph it, I would get a graph that looks something like this. Half of a sideways parabola. So that does pass the horizontal line test. And it says if it does have an inverse, then you need to find it and state any restrictions on its domain. So the first thing we do to find its inverse is we get rid of the f of x notation and I replace the f of x with a y. Then what you have to do is you have to switch the x and the y. And then you need to solve for y. So in this particular problem, I would square both sides. Then I would add 4. And now that I've got y by itself, I can use our function notation to indicate that the inverse is x squared plus 4. So that is the inverse. Now, this last piece that says state any restrictions on its domain. Here's how that works. If we go back to the original function, you can see that the domain of this function is numbers greater than or equal to 4. You can see that that graph is drawn from 4 to infinity. The range of this function is y values greater than or equal to 0. And you can see that that graph is drawn vertically from 0 to infinity. Well, the range of the original function becomes the restricted domain of the inverse. So my restricted domain here would be from 0 to infinity. If that's not quite making sense, think about this. Down below, I'm going to graph this inverse function that we just found. It's a U-shaped parabola curve that's been shifted up 4 units. Now, if you think about that, does that pass the horizontal line test? No, it doesn't. since it doesn't pass the horizontal line test, what we have to do is we have to restrict the domain and cut off part of this function until we restrict it to only being from 0 to infinity, and now it does pass the horizontal line test. And so this would be the inverse function with a restriction on the domain, and you can see how that compares to the graph of the original function up above. Let's move on to example 2a. Example 2a does have an inverse, and if I were to graph this, the graph would look something kind of like this. And that would pass the horizontal line test. The domain of that function is all real numbers. The range of that function is also all real numbers. So with that being said, the range of this function, all real numbers, is going to become the restriction on the domain of the inverse, and ultimately what that means is there is no restriction on the domain of the inverse here. So let's proceed to find the inverse. Let's get rid of the f of x notation. Then let's switch the x and the y. And then as we solve for y, we have to add 16 to both sides. And then to get rid of that cube, we have to cube root both sides. So I get y equals the cube root of x plus 16. To write it with my function notation for my inverse, I'm going to write it like this. And as I mentioned, there is no restriction on this domain. And that's because if we were to graph the cube root of x plus 16, it would pass the horizontal line test and there would be no restriction on that. More of the same, continuing with example 2, just a different problem. Example 2c, same directions. Determine if f has an inverse function. So we're going to go to the graphing calculator for this. If we go to the graph, you can see I've got the equation entered, the square root of x squared minus 20, and its graph would look like this. And you have to ask yourself, does this pass the horizontal line test? And clearly it does not. So since it does not, we just say it has no inverse. And since it has no inverse, we don't need to proceed and try to find its inverse. Next example, same directions. We'd start off by asking ourselves, does this have an inverse? So we're going to go to the graphing calculator again. And so you can see I've got the equation entered, x plus 7 over x. And if I graph it, my graph looks something like this. Now this is not a continuous function. The domain of this function is all numbers except for 0, and that should make sense because what happens if I put a 0 in for the x's? You'd get 7 over 0, which is not a number. So that's the domain, is all numbers except for 0. And the range of this function is all numbers except for 1. And here's how I know that. If I were to put a horizontal line at 1, you can see that this graph has a horizontal asymptote at 1. And so the blue curve will never touch the red line no matter how far to the right you go or how far to the left you go. So that is the range of this function. So keeping that in mind, since the domain is all numbers except for 0, and the range is all numbers except for 1, there is going to be a restriction on the domain of the inverse here, and that restriction should be the same thing as the range of f of x. Now let's proceed to find that inverse function. Get rid of the f of x notation, switch the x and the y. Now when you've got a fraction like this, what you want to do is get rid of that fraction by multiplying both sides by the LCD. Now I've got 3 terms, 1 on the left and 2 on the right. 2 of my 3 terms have a y variable in them. So what you need to do is get the 2 terms that have a y. You got to get them on the same side of the equation like I've done here. Next, you're going to want to factor the y variable out. And if I factor the y variable out, it leaves me with an x minus 1. And then I divide both sides by the x minus 1. And so my inverse function would be 7 divided by x minus 1. And you can see that the restriction on this domain is going to be all numbers except for 1. because what happens if you try to put 1 into the inverse? You get 7 over 0, and that's not a number. So there is your inverse and the restriction on the domain. Last example here, we have same directions but a different kind of function here. So what we're going to do is we're going to start off by graphing that. And so as we go to the graphing calculator, here I've got the equation entered, x minus 1 over x plus 2. And if we graph it, you can see again this is a discontinuous function. We've got a vertical asymptote at -2, because what happens if I try to put -2 into this function? I'd get -3 over 0, and that's not a number. And then I have a horizontal asymptote at 1 as well in this. So if I were to put a horizontal line at 1, you can see that this graph will never touch that red line, no matter how far to the right or how far to the left you go. And so, again, my domain is all numbers except for -2. My range is all numbers except for 1. So the inverse of this function should have a restriction on it, and it should be the same thing as the range that I just wrote. So our first step is to get rid of this function notation. Switch the x and the y. And now you have to multiply both sides by the LCD. That gets rid of your fraction. Now we want to distribute the x. Now I've got 4 terms. I've got 2 terms on the left, I've got 2 terms on the right. 2 of these 4 terms have a y variable, so we've got to put those 2 guys together on the same side of the equation. Everything else needs to be on the right-hand side. Now that's going to allow me to factor a y variable out. And after I factor the y variable out, I can divide both sides by the expression x minus 1. And that gives me the inverse to be -2x minus 1 over x minus 1. There's my inverse. And then the restriction on the domain is going to be all numbers except for 1. Last thing I'd like to discuss is the relationship between a function and its inverse. So you can see here this particular graph is a cubic function, and if we took some coordinate points such as 0, 1, another coordinate point would be 1, 2, and another coordinate point would be -1, 0. If we take those coordinate points, we can interchange them, and so the coordinate point 0, 1 is going to become 1, 0. The coordinate point 1, 2 is going to become 2, 1. The coordinate point -1, 0 is going to become 0, -1. And that allows me to draw the inverse, which looks like that. Now the relationship between a function and its inverse, it should be symmetry about the diagonal line y equals x. And you can see that relationship here. Those do appear to be symmetric about the diagonal line y equals x. One more example, this one's just a linear function, so if we take some coordinate points such as 0, 3, or another coordinate point as -2, -1, they would become 3, 0, and -1, -2. And so if I take those 2 points and I connect them, that would be the inverse. And again, the relationship that you should see is symmetry about the diagonal line y equals x. And those 2 functions appear to be symmetric about that diagonal line. So it's pretty simple to graph an inverse. Last one here. If we've got half of a sideways parabola, its inverse would be half of a parabola going up and to the right, kind of like this. I didn't take a lot of coordinate points, but as you can tell, these 2 graphs are symmetric about that diagonal line y equals x, and there is the graph of the inverse.